easier way than the dots, and that is to just consider the charges. We now know that we can tell charges for many substances straight from the periodic table. Anything in column 1, first group of the periodic table, would be a +1 type of ion if it's found in a chemical compound. Anything in group 2 would be a +2 type of ion. How do we know that? Because they relate to the noble gases. They go back to what do they have to do to become like a noble gas in terms of electronic structure. And these guys would lose 1 electron, these guys would lose 2 electrons. For the moment, we're skipping over the transition metals. We'll attend to them a little bit later. And then on this side of the periodic table, the halogens would be a -1 type of ion because they would gain 1 electron to become like a noble gas. Oxygen's family would be a -2. Nitrogen's group, a -3, and so forth. So we can tell that, and then all we have to do to form chemical compounds is to realize that nature demands electrical neutrality. What does that mean? Well, if I have 2 substances, sodium and chlorine, and I'm going to make a chemical compound from these, I consider what their charges would be in the compound. Sodium would always be a +1. Chlorine would always be a -1. Now what I do is I take a look and say, how many of these do I need to put together so that I'm matching the positives with the negatives? I'm trying to get a total charge of 0 by summing them up. Or another way to say that is an equal number of positives and an equal number of negative charges. In this case, it's a 1-to-1, so it's perfect, and it becomes NaCl. If it were magnesium and chlorine, magnesium is a 2+, chlorine a -1. So a 1-to-1 does not handle this situation. If we put these together as a 1-to-1, we would still have extra positive charge because we only have 1 negative. So the answer is we need 2 negative charges, and the way to get that is to take 2 chlorines. So the correct formula would be MgCl2. If I had magnesium and oxygen, I look at what those charges should be. Magnesium in group 2 would be a +2. Oxygen over in oxygen's family would be a -2. And here again we see that a 1-to-1 matchup works. Because I've got a +2, a -2, those charges match each other. And so it's just a 1-to-1 combination. And the formula would be MgO in this case.
I have a question.
Yes.
Right there, are you talking about the charge itself for that element?
I'm talking about the charge that the element would have if it were an ion.
Okay.
Okay, and when it's in a compound, it's going to be an ion. So if I'm making a compound, I want it to act like an ion. So I'm asking the question, what would it be like as an ion? Okay.
So you're saying magnesium has, because it has 2 valence electrons,
Right.
it's gonna have a positive.
It's going to lose both of those electrons. That's its tendency.
Right.
To lose both of those electrons to get the noble gas configuration of neon, and that would make it a +2.
Okay.
Okay? So aluminum, over there in group Roman numeral 3 or group 13, looking at the last digit in that 13, has 3 valence electrons. So what will it do? It'll lose 3 electrons and become a +3. If I want to pair that up with oxygen, which has a -2, ooh, now the math becomes a little harder. I've got a +3 and a -2. What combination do I need to take those in order to achieve electrical neutrality? Will a 1-to-1 do it?
No.
No, clearly not. So how do I decide? I can't do the math. How do I figure this out?
Do you do these are common factors?
Yeah, you're looking for a sort of a common denominator. Let me try some visual aids. I'm going to change my problem. Make it sulfur -2 instead of oxygen because I have sulfur carbs. Okay. Okay, so here is an aluminum. And this card represents aluminum, and notice that there are 3 notches out of the side of the card, and that means it's lost 3 electrons, and so it has a +3 charge, like we expect for aluminum. Here is sulfur. Sulfur is a -2 charge, and that means it has gained 2 electrons, so you'll see 2 bumps on this side. So if I'm going to put these together into a compound, will a 1-to-1 combination satisfy everybody?
No.
No. Clearly, what's missing?
Another sulfur.
You need another.
I need another electron here. The problem is, sulfur will come along and supply that electron, but he says, I got to supply 2. So now, if I pair that up, do I have a match made in heaven?
No.
Now what am I missing?
Another aluminum.
I need another aluminum. And aluminum says, okay, but I'm going to give up 3 electrons to do it.
Now one more sulfur.
Situation looks like it's getting worse. So what do I need next? Another hand is what I need. Ta-da! Does that make it?
Yes, it is.
All right.
It's
Yeah. 3. Okay, so our correct formula here is going to be Al2S3. Yes?
Well, the target will like, since AL is 3, 3 goes to the S and the S is 2, well, the goes to the AL. Will that always happen?
I hate that. I hate that. It'll happen, but careful. Look here.
Well, yeah, that's it. They're even, so.
Right. So the thing you have to remember if you're going to use that crisscross technique is that you have to reduce it to lowest terms. But otherwise it should work. I just hate it because I think people do it without knowing why it works and instead of trying to understand what's happening. But if what she's saying is that if you crisscross the numbers here, it actually gives you the formula. You didn't hear that from me.
Is that okay? So that is every time.
Yeah.
No. If it's if it's larger numbers, then you have to reduce it to simplest terms.
Oh, okay.
Okay, so if I have a 2 and a 2, if you crisscross them and get a 2 and a 2, that's wrong. It would be a 1 and a 1. Okay. What if you had a 4 and a 2?
It'd be a 1 or a 2.
Yeah, you have to remember to reduce
Oh, I
it.
like that. I like it.
Of course. Easy way out.
Just saying.
All right. So, what we're looking for is electrical neutrality, trying to balance those charges. And if we do that, then we have a correct formula for a chemical compound. And that's important for us. Now, when these substances make these ionic compounds, they attract each other in all directions. In other words, a positive 3 ion doesn't just attract the -2 sulfur directly, but it attracts things all around it. And so, typically speaking, in these solid materials, is that they are not discrete individual particles like Al2S3, but instead they form what are called a crystal lattice. Now, I can show you a good example of a crystal lattice with sodium chloride. Sodium chloride, ordinary table salt, is also an ionic compound and therefore forms an arrangement of the ions, which we call a crystal lattice. So, coming up on the board here is a slide that shows you how you would find these ions arranged together. You wouldn't find just one sodium and one chlorine tucked off in a corner somewhere having fun with each other. Instead, what you find is a sort of a global arrangement of these particles. As this is coming up here, focus on a sodium. Here's a sodium in the center. And notice that they're using actual girders here to show the bonds. But there's a bond to a chlorine in front, a bond to a chlorine behind, one to the left, one to the right, one to the top, one to the bottom. So there's actually 6 chlorines surrounding every sodium. Does that mean it should be NaCl6? The answer is no, because if you look at a chlorine, focus on one chlorine, you find that it has a sodium to the left, a sodium to the right, one above, one below, one in back, and if this continued here, we'd have another one out in front. So the ratio truly is 1 to 1, but they are arranged in this ordered arrangement of the particles called the crystal lattice. Now this is not what we would expect it to look like. If we could find that secret government lab where they had the shrinking rate, and they could shrink us down to a very, very small size so we could look at a salt sample, we would expect it to look like this. Fuzzy spheres, which is what we pretty much think atoms would look like if we could actually envision them. But notice how the spheres are very orderly arranged, kind of like the oranges in the grocery market when you go in there and they're stacked into that pyramid shape. Very ordered arrangement of the particles. In fact, this ordered arrangement lends itself macroscopically to the salt. If you look at salt, what do you see? White particles. If you look closely at those white particles, you'll find that they are not randomly shaped little white particles, but they are perfect cubes. They have very smooth sides, very sharp edges, pointy corners. And it's because of this crystal arrangement, this crystal structure, the lattice, as we call it, that gives the macroscopic salt crystal that formation. So your homework assignment tonight is, right after class you can do this, go to the cafeteria, steal some salt, dump it down on the table, and take a close look at the salt particles. And see if I'm not telling the truth, that those particles are tiny little cubes that have very smooth sides, very sharp edges, pointy corners, because of the crystal structure of the sodium chloride. And so that's how we find these ionic materials. And what we're actually describing to you by writing the formula down here on the board is actually called the, not the molecular formula, but just sort of the ionic formula, indicating that the ratio of sodium to chlorine is 1 to 1. But in truth, that little tiny piece of salt that you're going to dump out on the table is in effect one molecule. It's one huge molecule that's got tons of sodiums and tons of chlorines that make up that crystal structure. So we look at the formula unit. All right, so now we should have the ability to form ionic compounds just by looking at the charges that are involved, matching them up in electrical neutrality, making sure that the positives equal the negatives, however we want to do that, if we want to exchange the indices. Another way you could do this is you could say, okay, I'm going to take aluminum and sulfur. What's the total positive charge here? 3. Total negative charge here?
2.
Negative 2. Okay. Do those match? What do I need more of?
Both.
I need more of the negatives, right? So I've got to take another sulfur, which comes as a negative 2. What's the total positive charge now?
Positive 1.
Plus 3. What's the total negative charge? Do those match? What do I need more of? You need a 3. So I'm going to take the aluminum, get another plus 3. What's the total charge here? Plus 6. Here. Do those match?
No.
What do I need more of?
Sulfur.
Total positive charge. Total negative charge.
Mm-hmm.
We found the match, okay? So if you do a little trial and error like that, you'll get it every time. If you work until you get the match of positives equal to negatives. And then you look at it and say, the formula must be Al2 S3. And we can come up with that combination. Now, a little later, maybe today, if not today, then Thursday, we're going to take a look at the other kind of bonding, which is called covalent bonding. And when covalent bonding happens, there's a sharing of electrons. And in a sense, we can almost do that now. If I took nitrogen and hydrogen, for example, and I said, I'd really like to form a compound between nitrogen and hydrogen. We can almost do this 2 ways. What's the charge on a hydrogen going to be if it's in a compound? Plus 1. What's the charge on a nitrogen going to be if it's going to be in a compound? Minus 3. So if I have a plus 1 and a minus 3, how would I stick these together, in what relationship, what formula, to get a neutral compound? I'm going to take 3 H's and the N, H3N. All right, if I do the dot picture for this, I can also come to that realization. Because when I do dot pictures, what we're going to learn, and we haven't focused on dot pictures a lot yet, but we're going to look at the valence electrons. How many valence electrons does nitrogen have?
I'm sorry.
How'd you know it was 5? All you have to do is look at the periodic table and say, what group is this in? If it's a Roman numeral, it's a 5. If it's not a Roman numeral, it's a 15. We look at only the second digit. And we say, aha, there are 5 valence electrons. Now, we established a rule early on that said if we're going to put electrons around here, kind of like Hund's rule, what do?
One at a time.
Right, one at a time. Go around 1, 2, 3, 4, 5. Now, what I'm trying to do is to achieve an octet. And that means a set of 8 electrons around that nitrogen. And I'm going to do that by bringing in hydrogens. Well, how many hydrogens would I need to accomplish that? Exactly. 1 here, 1 here, and 1 here. Look at that picture. The nitrogen is totally satisfied. It's got an octet. The hydrogens each have 2. Remember, they're an exception. They have a duet rule. So they've got their 2. So is this a match made in heaven? Perfect. And look, it's the same formulation that we came up with the charges over here. Now, the reason I wanted to do this at this point was to take a look at this picture and talk about this thing right here. This is called a lone pair of electrons. Very appropriate name. Because why? The electrons are a pair and they're just hanging out there alone. So it's a lone pair of electrons. And they're just sitting there. They complete the octet, and that's perfectly valid. This works great. But here's my question. Do you think that that pair of electrons could be shared with something that was looking for 2 electrons, even though the nitrogen supplies both of them? Say yes. Yes, it could. So what is such a thing? How about a hydrogen ion? How many electrons does the hydrogen ion have? Careful.
1.
None.
0. Because the hydrogen atom has 1. The hydrogen ion means we have
Oh, yeah.
ripped off the electron and it has none. To be like the noble gas helium, how many would he like to have? All right, here he comes, walking on over here, and bonk. Fits in that position, bonding with those 2 electrons, sharing them. He reaches his noble gas electron configuration. Should this be a good picture?
Yes.
Almost. Except he brought in a positive charge, and that positive charge has to remain with the entire group. What I've just created, I'm on a roll, hold on. Don't forget it. What I've just created is called a polyatomic ion. Polyatomic ion. What does the term poly mean?
Many.
Many. Atomic, atoms, many atoms making up an ion. And there are many of these in chemistry. Several of these. Okay, now, yeah.
So you mean to tell me in that situation, hydrogen got rid of its electron, but it's now it got rid of its electron to be a positive ion, and by piggybacking off of the nitrogen, because it has a +2, it hits that noble gas status.
I agree with almost everything you said.
Yeah.
Hydrogen got rid of its electron, became a positive ion. Okay? And he's piggybacking off the nitrogen, but not because nitrogen was a +2. The nitrogen was a neutral compound. It had a lone pair of electrons sitting there. Remember, those electrons are actually negative. But the whole group is neutral. Positives and negatives match. The hydrogen is going to come in and occupy this position, but he's bringing in with him a positive charge that we can't lose. So that positive charge is now distributed or attached to the entire particle.
So it makes the entire entity positively.
Yes.
Okay.
Yes. Yes, ma'am.
Okay, so before you brought the extra hydrogen, the outer shell was full, right?
Yeah.
So I don't understand how can it come into the compound when the outer shell was full. If it's full, you can't like add any more to it, right?
I'm not adding any more electrons to it.
So how could it?
All I'm doing is sharing those electrons now with some guy that doesn't have any. Okay?
What I mean, can you?
Exactly.
So you saying?
We'll work for electrons.
So you saying the hydrogen doesn't have any electrons?
I'm saying that.
But no, it kind of makes sense because the ones that bonded with the nitrogen had electrons.
They
Right?
did.
So why?
Okay.
What?
Well,
made
can't
that-
I talk about two different guys?
Yeah.
Okay. So I've got three of these guys who have an electron. They came to the party, joined in. Okay. Here's a guy that squandered his electron. We don't know where, but gave it away somewhere and said, "Gosh, I wish I could join the party." And the nitrogen is saying, "Well, actually, we got two unused electrons here just hanging out. Why don't you come in and share them with us?" So he comes over and shares, but then he brings his positive charge along with him. That's all that's happening. You don't like that?
It kind of don't. I get what you're saying, but maybe I'm just being too like literal because I don't understand why those are negative but that one is positive.
Who's negative?
The hydrogen.
No, they are not.
I mean, it was positive, but that one.
Hold
the
on.
other one-
These guys are not negative, they are not positive. They are neutral. They have one proton, one electron. The nitrogen was neutral. He had 5 valence electrons, but 2 in the 1s, so he's got 7 electrons total and 7 protons. We're talking neutral substances here. They share electrons and create a neutral substance, NH3. Okay? This is the only guy that's got a charge, and he's got a positive charge. Which, if we view that in terms of electrons, means he's lost his electron. If he wants 2, all we're saying is that this gives him an opportunity to share these 2, because he's got none. So he can come in and share these, but he's got to bring his positive charge along with it. So it gives a positive charge to the entire entity. Okay? Now, yes?
So why does he have to bring a positive charge if it's going to be 2 electrons with 1 proton? Won't that be negative?
No. Because let's total up everything here. Okay? In terms of the nitrogen, what's the nitrogen bringing to the mix? Proton-wise. He's bringing 7 protons, right? Electron-wise, he's bringing 7 electrons. We only see 5 of them because we only look at the valence electrons. But if you look at the electron configuration, there's also a 1s2 that's completely filled. Okay? The hydrogens, the 3 of them, have a total of 3 protons, 1 for each here, and 3 electrons. Okay? The extra hydrogen ion brings what?
1.
1 proton and no electrons. Now, what's our total? 7, 3, 11 protons. And remember, those are positively charged. What's the total here? 7, 3, 10 electrons, and they're negatively charged. So do I have a match of positive and negatives? What do I have more of? I have to show it. Okay. That's where the positive's coming from. Right? These are important. And there's a few of them. And we need to know that. And so what's the alternative that we have for them? We have to memorize them. And there is a nice list you'll find on the website. It's about, I think it's only about 18 or 20 or so. that you have to memorize. And what's the best way to memorize these things? Flashcards. If you try to remember from a list, what happens is when you're doing the list and you're saying, okay, acetate, arsenic, and so you end up knowing the one before you get to it because you memorized them in order. So what can you do with flashcards? You can shuffle them, right? You can take them out of order. And how do you make up these flashcards? Front and back. On the one side, you write the name, sulfate. On the other side, you write the complete formulation for it. SO4 with a charge -2. You must know the charge associated with the group. So SO4 -2, just say it as one breath. SO4 -2 is sulfate, okay? So you make up a set of flashcards, it takes about 18, 20 cards like this, and you take them with you everywhere, right? When I come in here, instead of complaining about the heat, what are you doing?
Studying the flashcard.
You're flashing through your flashcards so fast that it's fanning you down, right? If you're waiting for the guy to open up the lab door, what are you doing? Okay, you're doing something in the lab, you're heating for a while. We don't talk about last night's date. Get the cards out and start doing your flashcards, right? Let's talk about a date. Your date comes to pick you up and he's late, huh? Flashcards. Date's not quite what you expected him to be. Doing the flashcards. No hurry. Tomorrow would be fine. Yes.
Okay, so look, to do that, to begin with, we have to know the electron configuration before we should do that. I mean, like,
No.
you got the answer without.
Just memorize.
I'm saying though, like, seriously, on the test, are there gonna be, is there gonna be some on there where we have to, you know what I'm saying? Or if
I do know what you're saying.
just memorize?
Just memorize.
You sure? Okay,
When we get to dot structures, we may take a look at one or two of them.
that's what I'm saying, I just.
Okay. When we get to dot structures, we may take a look at one or two of them, but we're gonna have a set of rules to do that. It's going to be very simple and straightforward. But for most of the stuff you have to do with them, you just
Can
have
we do
to.
some more of that though?
Yes, we can. We can. You mean,
But what you're doing with the dot, isn't that called dot configuration?
it is,
Okay.
and I'm, part of the problem I have is I can't do everything at one time.
Right.
So I gotta sneak ahead and pull something from the future and bring it back a little bit so we can get something underway here. I want to get these polyatomic ions to you because why? You gotta memorize them. And what does that take? I know it takes more than a day, right? Probably takes 2 days for you to get to them. So I want you to know them by the next exam, so let's get them out there today. Now, what are we gonna do with them once we have them? Well, remember what we were doing over here. We're gonna do exactly the same thing with polyatomics. So if I have a potassium and a sulfate, okay, then what are we going to do? Potassium is easy. You can go to the table and find out what its charge is. What's the charge on a potassium? +1. Sulfate, not easy. Because can you go to the table and find a sulfate?
No.
Doesn't exist there. It's a polyatomic. And where do the polyatomics exist? In the little gray cells up there. So when you see that sulfate, you've got to say, I know what that is. That is SO4 -2. And that's how you need to know it. Whole package. SO4 -2. It's not enough to know SO4. If you don't know the -2, you're screwed. Okay? So SO4 -2. Now, I'm treating this like a single entity. So, can I put a +1 thing and a -2 thing together?
No.
Why not? Okay, I can put them together, but I need 2 potassiums. So it would be K2SO4. Yeah, we're going to come up to rules probably later today too. And then you'll know why the potassium always goes first. There's actually a rule. My hand won't let me write it the other way. You could write it the other way at this point, and I won't yell at you, but my hand has been doing this for too long. Okay, so how about this?
Wait, don't go.
Sure.
Do you just, like, she had to say you just cross the charges?
Well, I'll never admit that in public, okay? Because I don't like that method. But that is something that works.
So why don't you like
Yeah, why don't you like it? It's so much.
Because I think people do it without knowing why it works. Okay, if I now say to you, okay, let's talk about the electrons, and what? The electrons.
Yeah.
I'm just crossing the digits.
I don't like that either, 'cause I don't understand it.
So I think it's kind of like a calculator. All right? I don't object to calculators. They're marvelous tools. But does that mean you shouldn't know how to do the math yourself?
Yes.
You should know how to multiply, divide, add, subtract yourself. Then using a calculator is a useful tool. But if you come to me and say, well, I don't know how to multiply by 1, I got to use my calculator. No, that's very sad. All right, let's try another one. All right, let's try this. Calcium.
Phosphate,
What is calcium? What charge?
positive.
Positive 2. How'd you know that? Because it's in group 2 of the periodic table, so it must be a +2. So calcium +2. Phosphate. I don't know. Yep, it's one of our polyatomics, which we will know in a day or two. It's PO4 -3. So phosphate, PO4 -3. So what would our correct formula be? We'll see A3.
Yeah, we'll parentheses. And then, yeah.
So do you see why I need parentheses sometimes? Because the parentheses are maintaining the integrity of the polyatomic ion. And I need to know that. So can I write this as just P2O8? No. I don't want to do that. Because then somebody will not recognize it for what it is. It's actually the phosphate ion.
Is that for a subscript?
For a what?
Subscript. Is that subscript?
This one?
Yeah.
Yes, that is a subscript. My bad.
How do you get to that?
Well, let's do it like we did before. Calcium and phosphate. Will a 1-to-1 combination of this give me a electrical neutral combination? What will I have more of? If I got +2 and -3, I've got more negatives, which means I need more positives. So I have to take another calcium, because that's the only way I can get more positives. Now, what's the total positive charge I have? +4. Total negative charge? -3. Do those match? Which do I need more of? Positive or negative? Negative. The only way to get more negative is to take another phosphate, which comes as a -3. Now, what's the total positive charge here? What's the total negative charge? Do those match? Which do I need more of?
Phosphate.
The only way I could get more positive is to take another calcium. What's the total positive charge? Total negative charge? That's the match. And so Ca3, PO4, 2. Yes, ma'am.
Just so I'm sure, to get the charge on the substance that we can't find on the periodic table, it's always in the water? Or where do you get that?
It's always answer to the question, what does this guy have to do to become like a noble gas? So look at magnesium. He's element number 12. Who's the closest noble gas to him? Just look at the numbers. Let's go back to neon. So that means he has to lose 2 electrons. And if he loses 2 electrons, he becomes a +2 ion. Because remember, electrons are negative, and that would leave an extra 2 positive charges. Okay? Question? Yeah. Oh, sure. We're going to take aluminum and hydroxide. So the first thing you need to tell me is, what's the charge on the aluminum?
Plus 3.
So aluminum's going to be plus 3. The second thing I need to know is, A, what is hydroxide and what's the charge on it? Now, at this point, you haven't memorized these things, but you can also find them on page 129. Page 129 of your textbook also has them listed there. Well, the ones on the sheet on the web are the ones you have to remember. The one in the book might have a few extra. Okay? But hydroxide is OH negative. So I have to come up with a combination of these things that's going to achieve electrical neutrality. We're bad. Yes, ma'am. Because there's only one sulfate there, so there's no confusion. I don't need the subscript 1. So the only time the polyatomics are put in parentheses is when there's more than one of them. Yes, sir.
Can you do the dot electron diagram for that?
For what?
Manually?
Yes, I can. Do you want me just to do it to show you that it's there? Because we haven't really established the rules for doing dot structures yet. And the rules will make it easier. But I can show you the dot structure. Sulfur, for example, has 6 valence electrons around it. Oxygen has 6 valence electrons. And so I'm going to put 4 oxygens around the sulfur like this. Okay? Now, there are 2 spots that don't look very good yet because these oxygens don't have an octet. But remember, the sulfate ion comes to us as a -2 ion. What does that -2 mean in terms of electrons? 2 more electrons. So 1 there, 1 there. And so now the dot picture is
We haven't got,
a work of art. We haven't gotten what?
we haven't got that yet.
No. We're inching toward it. All right? Okay? Other questions? Yes.
When you were talking about the polyatomic, ions, what are those used for? Like,
For making chemicals.
and like all the chemicals that we've made today, are they actually used? Like I know sodium, of course, is
Are
table
they real
salt.
stuff?
Yes,
Yes.
sodium chloride is
Yes.
table salt. Okay.
We can find them in most labs.
Okay.
Okay? Now, realize we've been building and getting you to write chemical compounds. And the question always comes up, well, how is this going to be on a test? What are you going to tell us to do? Are you going to tell us to take aluminum and take hydroxide? No. What I'm going to do is give you the name of the chemical substance. So what we want to do now is to talk about how do you name these guys. Because once we name these guys, now we can flip-flop. Look at a formula, get a name, look at a name, get a formula. And that's the way it'll appear on the test. You'll have a set of names, you have to write the formulas. A set of formulas, you have to write the names. So what are the rules for naming? In the early days, there were no rules for naming. People just called things what they wanted to call them. For example, even today, what's this?
Water.
Water. That's not a very chemical name. What does that mean? We're not going to change anybody's mind and have them start pronouncing this in terms of the elements that make it up, the chemical name. And so we deal with what are called common names on occasion. But when chemistry started to get rolling a bit, they realized we can't continue to call everything by a common name. Because today there are over 50 million compounds known, and do you want to memorize 50 million different common names for compounds? Or should we establish some kind of system, some kind of set of rules? And so what we did was we locked some chemists in a room and told them they couldn't come out until they came up with a set of rules that made some sense. And these guys were called the International Union of Pure and Applied Chemistry. And so we have what are called the IUPAC rules for naming chemical compounds. And so what we're going to do now is to go over the IUPAC rules for naming chemical compounds. These are what the guys in this room decided would be most logical. Rule number 1, the positive ion is always written first. So the question was asked earlier about putting potassium first. That's why. It's a positive guy. The positive guy always goes first in both the formula and the name. And so if you look at my examples up here, we pretty much followed that. Sodium is the positive guy, we got NaCl. Magnesium is a positive guy, we got MgCl2. Magnesium is a positive guy, MgO, and so forth. The positive is always written first. Rule 2. The name is made up of both ions. So they're going to have a first name and a second name. The first name is usually just the name of the element. Most frequently that's a metal, because the most common occurrence of ionic compounds is a metal with a non-metal or a metal with a polyatomic ion. And so it's almost always a metal that's a positive guy. And so the first name simply becomes the name of that element. The second name varies a little bit. If it's a binary compound, what's a binary compound? Binary compound means 2 and only 2 elements. Then what we do is we change the ending of the second element to IDE. If it's a binary compound, we change the ending of the second element to IDE. So let's take a look back at salt. All right. The name for this is, first name, sodium. Second element is chlorine. We don't call it sodium chlorine, we call it sodium chloride. So we've changed the ending of the second element to IDE because it's a binary compound. There's only 2 elements here. So let's go down our list up here. How about the magnesium and chlorine compound? Magnesium chloride. Here. How about this one? Magnesium oxide. We're changing the ending to IDE. Aluminum sulfide. We're skipping that one. Oh, that's not a binary compound. All right, what if it's not a binary compound? What if there's more than 2 elements? Then you're probably dealing with a polyatomic ion. And the name simply becomes the name of the polyatomic ion, which you have memorized. Exactly. So, if I combine potassium with sulfate, my compound that I make is potassium sulfate. If I combine calcium with phosphate, I make
Calcium phosphate.
calcium phosphate. If I combine aluminum with hydroxide, I make
Aluminum hydroxide.
aluminum hydroxide. So there's no mystery here in the naming. Once you've memorized the polyatomics, all you have to worry about is if it's an element from the periodic table, I'm going to change the ending to IDE. Now, can we complicate things? That's what chemistry's known for, right? Transition metals. We've avoided them like the plague so far. And for good reason. The problem with the transition metals is that when we look at a transition metal, I cannot tell the charge. If I look at a group 2 metal, can I tell the charge? +2. All right? Get out of here. First group, +1. No question about it. Transition metals, not so easy. Why? Well, there are some weird things that happen. Remember, they're filling d electrons. They got some other things going on. It turns out that we can end up with more than one possible stable ion for them to exist as. Copper, for example, can end up as either copper +1 or copper +2. Iron. Iron can turn out to be iron +2 and iron +3. Some of them can have as many as maybe 5 different possible ion states that are possible to use. So, if I say to you, all right, I want you to make a compound between iron and chlorine, what's your question going to be? You're going to ask me which iron. And for you to do it correctly, what do I have to do? I have to tell you. And if I have to tell you, is there anything for you to learn? It's that easy. I'm going to have to tell you what the charge is. Okay.
Are you going to tell something?
Yes, ma'am. I'm going to tell you. Now, how am I going to tell you? I tell you because it's part of the name. Okay? When I write the name, let's say it's iron +2 and chlorine, which is a -1. All right? Let's write the formula first. Okay? The way I would write this name is that this is iron 2 chloride. In other words, the Roman numeral is an integral part of the name. And the Roman numeral tells me the charge on the metal ion. Okay, you got to write this down. The Roman numeral is the charge on the metal ion. The Roman numeral is the charge on the metal ion. If you have a highlighter, highlight that statement. The Roman numeral is the charge on the metal ion. Now, let me tell you what I did not say. The Roman numeral is not how many there are in the formula. Students get this confused all the time. It's not telling you how many there are. What does it tell you?
The
Charge on the metal ion. So if I say to you, iron 3 bromide, is that enough information for us to write the correct formula? Should be. What do we come up with? Or how should you do this? It's a test question. How should you do this? Probably take some scratch paper, and on the scratch paper say, okay, what have I got here? I've got iron. First of all, I have to know that's Fe. Aha! Remember I gave you a list of elements for the first test?
Yes.
Still true. You need to know them. So if those flashcards haven't worn out yet, get those out and start snapping through them again. So iron is a +3. Simple as that. I'm just reading it straight from the name. Iron's a +3. Bromine.
Minus. No, alright.
Minus. Just minus.
Minus or -1, yes. Okay, now I've got to put these together into a neutral chemical compound. That's my job. what would it be? Br3. Exactly. Now, the bad news is, we also have to do this backwards. Okay, so in other words, so this is copper 2 chloride. I don't want the minuses in there. I'm writing the name. And the name has to end in IDE. All right, how about this one?
Is it? Still up here?
What's the charge on an oxygen? Oh, that was That's great, but that's not what I asked. I asked you what the charge on the oxygen would be. And it would be -2. If it's -2, and there's only one copper here, what must it be for this to be an electrically neutral compound?
2.
Must be a +2. Yeah. Yeah.
Can you say how that was 2 again?
Sure. What's the charge on the oxygen? Look at the periodic table. What does oxygen have to do to become like a noble gas?
Oh, okay. She don't remember that.
Well, now you're on the shopping block. So, what does oxygen have to do to become like a noble gas? It has to gain 2 electrons. That means the oxygen is going to be -2. So what must the copper be if, when put together, these things total 0? Must be a +2. Okay. The metals?
Yeah.
No. The metals will always be positive. Okay? First of all, they're always going to occur after the first guy, and you know what the first guy is always the positive guy. So that shouldn't be a problem. So, how about this one? Let's try to name this compound.
That's phosphate.
And cobalt. Cobalt phosphate.
It's going to be cobalt something phosphate. I got the cobalt, I got the phosphate. Let's see if we can figure out what it is. What is the charge on the phosphate alone? -3. So if there's 2 of them, the total negative charge must be +6. For this to be neutral, what must the total positive charge be over here? +6. If I've got 3 cobalts, what would each cobalt be so that together they gave me a total of +6? Be a 2. Tell them we're busy. Mhm. What is a single phosphate? What charge? If there's two of them, what's the total negative charge? -6. Okay, so what must the total positive charge be over here? For this to be neutral, it's got to be a +6. If there's 3 cobalts, what would each cobalt be to give me a total of +6? Wow. Yes?
Can we just look at the two behind the phosphates?
I wouldn't. I wouldn't, because if you just look at the 2 back there, it's not always going to translate. Because look at this. Would you look at the 1 here and call this copper 1? So, again, a good rule of thumb is don't make up your own rules. Okay? They generally get you in trouble. Yes?
Is this how you make them?
Well, that's how you name them. In order to make them, we're going to have to get to the chapter where we deal with chemical reactions and actually mix them with something to make these substances. But this will be a good thing to know when we get there, because in order to make substances, we have to know what the formulas are and what they're called. Yeah.
What is our test?
I don't know. What is it, after chapter 4? Or is it after chapter 5?
After chapter 4.
Yeah, so we're in 4 now, so I don't know.
We got it next.
We'll do it next week?
How about the
No.
15th?
We can-
How about the 15th? That'd be a good.
No, the meeting- our body's right on the 14th.
Okay, why not have it there?
That'd be fine, we could meet somewhere, we could meet at Barnes and Noble and set up an exam then, that's fine. We'll talk about it probably Thursday.
Next week.
Yeah, maybe next week, yes.
How do we know phosphate was -3?
Because you memorized it.
Okay,
It's a polyatomic ion,
okay,
and you memorized that it was -3 when you made your flashcards.
gotcha.
How are we getting 2 for copper?
How am I getting 2 for copper?
Yeah, like
Well, what's a chlorine?
chlorine is 2, right? What do you, I don't know.
What's the charge on a chlorine?
-1.
What does it have to do to become like a noble gas?
Well, add 1.
And if it adds 1, what's its charge? -1. How many do I have?
2.
So that's a total of -2. So what must the copper be in order for this to be a neutral compound? Don't look at the table, look up here.
-1.
So a -1 and a -2, a +1 and a -2 will total 0?
No, so that's good too.
I agree. So it's copper 2. Yeah.
I thought for it to become as a noble gas, then we had to subtract the Roman numeral from the noble gas.
You thought wrong.
That's wrong.
Yeah.
Okay. How do we determine for it to become a noble gas again?
You count electrons.
Okay.
How many electrons does chlorine have? Valence electrons.
7.
7. So what does it do to become like a noble gas, which has 8?
Okay. Then it has to gain 1.
It gains 1, and so then it's a -1
Gotcha.
type of charge.
Thank you.
Any other questions?
I have a question.
Yeah.
So with this whole thing, we have to know the charge of the what is it called? The polyatomic ion?
Yes.
So we have to know those charges, and then from that charge, make the other element neutral with that charge.
Well, the compound is going to be neutral. Okay. You have to say, all right, if the compound is neutral, then having this number of metal ions, what would their charge be so as to match the number of polyatomic charges that I have? Does that make sense?
Yeah, it does. I don't know. It's just like doing it, for the first time.
That's why you should practice. And do we have tools to allow you to practice?
Yes.
Yes, we
Question,
do.
Dr. Brown.
On the website, you'll find out a sheet like this. Let me explain what the sheet is. You've got positive ions across the top. Now, some of those positive ions, the charge is given to you. Copper, there's a +1 up there. Why am I doing that? It's a transition metal. I have to tell you what it is. Aluminum, I didn't give you the charge. Why not? You can tell that from the periodic table. Okay? And so there are positive ions across the top. Down the side are the negative ions. I didn't give you any of those charges because A, you can tell them from the periodic table, like chlorine, -1, or B, they're going to be polyatomics, and you're going to memorize what those charges are and be able to fill those in. Then wherever a row and a column meet, like here, aluminum and let's go to nitrate, you would say, all right, I want to make the formula for aluminum nitrate. And so you write out the formula, correct formula for aluminum nitrate, and you can do the name. Write the name for aluminum nitrate. Aluminum nitrate?
No.
Practice writing names and formulas, not on the website?
It is.
My people say it is. All right, are there other things that are available to us? Yes, there's a list of polyatomic ions that you can use. Yes, ma'am. Use what? We will. Not yet. He's more a covalent bonder, so we'll get to him. All right. There are. Oh, these are my sheets, not yours. There are sheets on the website that can be used for. Let me find them. Practicing names. Look, there's a sheet of about 25. You got formulas, and you write the names that are associated with it. And then when you've exceeded that, we have an identical sheet that is somewhere. Anyway, there's one that's got a bunch of names, and you write the formulas. So you got plenty of things to practice. Okay? And there's even some quizzes on there that give you even more practice. And we'll be doing a few in class here, like in a minute, so that we can get more practice with those. But the only way you're going to get comfortable with these is with lots and lots of practice. Now, back to the list of polyatomic ions. If you look closely at that list, you'll see that there's only one positive polyatomic ion. And that was the one that we used to start this whole discussion. It was NH4, +1, and it's called ammonium. But there's two others listed there. One is zinc and one is sulfur. They're not really polyatomics, not sulfur, silver. But they are transition metals. But they're transition metals that don't change. They are always fixed. So zinc is always a +2. And so since it's a transition metal, we want to memorize that it's always a +2. Silver is always a +1. So we want to memorize that silver is a +1. Now there's a bit of a trade-off. Tin and lead, these two guys, can either be +2 or +4, and they're not transition metals. But you will typically see a Roman numeral with their names because they can either be +2 or +4 as well. So there's sort of an exception there for them. All right, questions? Yes?
Do you write zinc and silver with the Roman numeral?
You don't need to. If you do, that's fine, but make sure you put the right Roman numeral. If you put the wrong Roman numeral when it's not needed, the red pen will fly. If you don't put the Roman numeral when it is needed, the red pen will fly. But if you put it and it's correct and you don't need it, that's okay. So how about we try about 3 of these? Now, if you have to, use your polyatomic ion sheet, or if you have your textbook, page 129, or copy from the person next to you if it's polyatomic, and see if you can come up with the correct names for these compounds. Does this need more time?
Yes.
All right.
Don't need the two, but it's okay that you put it.
Oh, I don't need it?
Well, see, it's a group two, it's always plus two. And if it's always plus two, then we don't need it. But if you put it,
Okay.
as long as it's correct, it's okay.
Never put the AP in row. It's part of the polyatomic. So remember, some of them will be self-take, some will be self-light, some will be nitrate, some will be nitrite. So you put the AP in, you have that. So it's nothing that you have to apply.
Right. Two. You just balance it out, but you don't need it because magnesium actually needs to get rid of it.
Okay.
So the plus two, so you don't need it.
Cause it's in the Roman numeral two. And then OH.
So that's why it's what we need to do.
Whole name system.
On that plus.
The chloride.
Ferrous, ferrous.
And then potassium.
That's from
Sulfur.
What do you get for last one? No, you're right.
It's already two.
That sounds right.
If this is a negative two charge.
It's right because it's a minus two.
So,
You balance.
alright. I'm asking.
Okay, are we ready?
Yeah.
Trade favors, grade each other?
Nobody could drink it.
All right, I get magnesium hydroxide. Yeah, I want to talk about spelling.
Oh, Lord.
All right, first one was magnesium hydroxide. Spelling, the spelling count. If it's multiple choice, then it's really not a problem because the spelling should be there. for you. If it's a handwritten type of thing like we're doing right now, I'm pretty lenient with spelling as long as I can make it out, but be careful. There is an element, number 25, called manganese. If your magnesium looks more like manganese than it does magnesium, then I gotta take off, okay? But as long as you got an extra E in your magnesium, I think, or something, that's doable, that's okay. We can live with that. Okay, yes, ma'am. Polyatomic ion? Yes, it is. And the name of that polyatomic ion is hydroxide. So that's why
So would you have to put the numbers like you did right there?
numbers like I did where?
Right there. Like if they got iron 2 chloride.
Chloride on the board right behind me. Iron 2 chloride.
Well, I have to put it for iron 2 chloride, but I don't have to put it for magnesium. Because magnesium is group 2, and that's always +2. So I don't need to put the Roman numeral. All right, second one is, I guess nobody should have missed this one. Isn't that on the board? Oh, iron 3 chloride. Yeah? And potassium sulfate.
Yeah,
When should we put the number?
You have to put the number when it's a transition metal.
Oh, okay.
That's your cue. If it's a transition metal, except for zinc or silver, you better put a Roman numeral. Who? The last one? Because what's the SO4 group name? Sulfate. I have to use its name. It's not a binary compound. There's 3 elements: potassium, sulfur, and oxygen. So the IDE doesn't apply to them. Okay? And you've memorized sulfate, and that's all you use. All right, how about next time I bring in a little quiz
Okay.
to start with, huh? About 5 of each or so, and we'll play with it. On names and formulas.